Okay, so this is the second session that we want to talk about this pigeonhole principle. And then if you remember, there were some problems left. So example number 7 is from the previous session, the same for example number 8. And I will add 2 more examples to this, and then we end this topic. Okay, so okay, who wants to answer this example? So let me read the example first. Each point of a given straight line is dyed by a color. I don't even know, is this a correct expression here? It's dyed by a color, so I'm painting it in a color that is randomly chosen from a collection of 11 colors. So we have 11 different colors, and then we have a straight line. When I say I have a straight line, it means that it goes to infinity from both sides. So definitely there are infinitely many points on this line. Each point is randomly colored by a color chosen from a collection of 11 colors. Okay? So that's the statement of the problem. And then we want to show that one can find 2 points of the same color on this line, even though this process is done randomly, on this line, whose distance from each other in meters, for example, is a natural number. So is the problem clear? So I have an infinitely long line, infinitely many points on this line. I randomly color each point in one color chosen from a collection of 11 colors. And the point is that it doesn't matter how this is done, I can make sure that there is at least 2 points with the same color whose distance from each other is a natural number in meters, of course. 2 meters, 1 meter, 3 meters, 10 meters, 1,000 meters, we don't know. But we want to guarantee that there are 2 points of the same color whose distance to each other is actually a natural number if this distance is expressed in meters. And there is nothing specific about meters. This can be kilometers, I don't know, centimeters, all of them. We can just cook an argument with yards, feet, and any other lengthy unit instead of meters. Okay, so I want to hear from you first. So what is your strategy to tackle this problem? Again, you see that this problem seems hard because I have infinitely many degrees of freedom. First of all, I have infinitely many points, and then I have 11 colors. So you see, it also adds to this infinite degree of freedom. So it seems a very violent problem. Yes, it is very hard to get things under control. This is the nature of these type of problems when you're dealing with pigeonhole principle. Okay. Who wants to answer this?
Does my mic work?
Yes.
Yes. Well, once you've investigated 12 points that are all a natural number of meters away from each other, then you're going to have at least one pair of colors.
Mm-hmm.
And those 2 pairs of colors are going to be a natural number of meters away from each other. 11
yes.
colors total.
Yeah, okay. So I understand exactly what you say, and I think that's right, but make it more tangible or more concrete. Let me just do it in this way. So for example, let us just draw a line here. So assume that this is your infinitely long line. It goes to be infinity from both sides. Okay, and then let me take, I don't know, a twig or whatever, a very thin, for example, stick, which is 11 meters. Okay, so this is the way that I imagined it myself. Okay, so for example, let me draw every one grid. I will take it 1 meter. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Okay, so assume that the length here, I am assuming that I have a stick of 11 meters. This is the way that I imagine it in myself, in my head. Okay, And then I have this point. I will consider these points. So how many points I have? I have 12 points, hopefully. Am I right? 1, 2, 3, 4, 5, 6. Yes, let me count it once. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yes? So if you see, I am just highlighting this in my head. Okay, I'm just doing it so that I want you to see this. I will take this meter stick and just throw it on this line somewhere. Okay, so we can, let me see if I can do that. So I will take this one. Yes, copy, and I will put it here, for example. Yes, I don't know where I put it. I just put it somewhere here. Is that clear what I'm doing? So I have infinitely long line, and I imagined in my head a meter stick of 11 meters, and I highlighted these points. So this is 1 meter, this is the second meter, the third meter, until the 11th meter. I take it in my head and put it somewhere on this line, wherever, it doesn't matter. Then how many points I am facing? I have 12 points. And these points now are on this line, and all the points on the line are colored in one of these colors from these 11 colors. But how many points are there? There are 12 points, but how many colors are available? I have only 11 colors available. So using the pigeonhole principle, it is guaranteed that at least 2 of these dots are of the same color. Is that understandable? I have 12 dots, so I have 12 pigeons, but I have only 11 colors, 11 pigeon holes. So it means that there should be at least 2 of them having the same color. Okay? And then it doesn't matter if these 2 are of the same color. The distance from this one and this one is how much? 1, 2, 3, 4, 5 meters, which is a natural number in meters. It doesn't matter, I don't know, if this one and that one are the points which are in the same color, then the distance from these 2 is a natural number in meters. So, but this is inevitable, yes? Because I have 12 points and only 11 colors, at least a pair of them have the same color, and it doesn't matter which pair are these points. The distance from these 2 is always a natural number expressed in meters. Is that clear? Hopefully this way of imagining it make it a little bit easier to understand. If you have any questions, please let me know. Okay. And then of course, I think it is clear that we have a lot of actually infinitely many points of these things, yes? Because I take this meter stick and now put it from here to here, then I will get another pair. Then I will put it, for example, here, then I will get another pair, yes? And I can repeat this process infinitely many times. So I can actually generalize this problem to saying that, okay, I have infinitely many pairs with this property on my line. Okay. So you see, I don't know, I really like these kind of problems. So the solution is very simple, but the way that you need to argue around that for this is actually quite interesting. Okay, what do you think about the next problem from the previous session? Let me read the problem for you first. 10 points are chosen from the interior of an equilateral triangle. Show that there are at least 2 points among the chosen points whose distance from each other is at most 1/3. Do you have any idea? Of course, I think the problem 9 was simpler. If I remember, I should have interchanged these problem 9 and 8. Yes, but I'm just waiting to listen from you.
What do you mean by 1/3?
You are right. So this problem is not correct. So why didn't you complete in the first place? Of an equilateral triangle of length 1. This is what I should have written here. So 10 points are chosen from the interior points of an equilateral triangle with side. Yes, thank you. I don't know why didn't you complain before. So with side, say 1 meter. So I would say 1/3 of a meter at the end. Yes. So that problem was not. Yes, that the problem needs this information. It's not clear. Yes. Now is the problem clear now?
Yes.
Okay. Yeah. So you should complain sooner. I hope that everyone actually realized that there is something going wrong. Yes. Okay. So now that we are here, if you don't mind, let me go to solve the next problem. I think the geometry of the next problem is a little bit simpler, which is the new problem. Then I will go back to this problem. So let me read this one. Hopefully I have done this correctly. So 5 points are chosen in the interior of a square whose side is 2 centimeters. Prove that there are 2 points having a distance not more than a square root of 2 centimeters. I think this problem have the same type needs the same type of reasoning, but this is a little bit simpler than the previous one. So we let us solve this one and then we go back to the previous one. So is the question clear? So I have a square whose side is 2 centimeters. So let me draw, for example, here for you. So let me consider each one of these 2 grids 1 centimeter. So let me take it 4 so that it becomes easier to see. So let us consider this square. Okay, so I am assuming that the side is 2 centimeters. The side is 2 centimeters. Then I choose 5 points here. This tells you that it doesn't matter how do you choose these 5 points. There is at least, usually the word at least and the randomly chosen are actually ignored in the statement of these problems. This is always the case. So we choose 5 points here. It doesn't matter if I do it randomly. Then definitely there is a pair whose distance from each other is not more than a square root of 2. Do you have any idea how to reason about that?
Yes.
Yeah. Anyone else? No one else?
I mean,
Do we look into the diagonal?
No. How? So because I'm listening to you. I'm not saying that the way that I am thinking is the only way. Might be you have a better way. So that's what I'm saying. So you need to tell me what is your argument, and do you really need a pigeonhole principle, or your argument is in a way that doesn't need pigeonhole principle at all? So if you want to answer, you need to say something, and I'm listening to you. And that is right. We accept it. If not right, I try to correct you. So do you want to continue yourself, Khulud?
No.
Not
No.
Okay. Okay. Someone else? Diagonal is a good idea, but of course, how you want to cook up your argument?
Mr. Babak,
Yes, maybe speak louder. I cannot hear you properly.
we know that the perimeter should
What?
be 8. We know that the
Yes.
perimeter of the square should be 8, right?
Yes.
And using that fact, we know that. Wait, I have to think about it. I just saw the problem now, so.
Okay. Anyone else? So Emil, if you want, you can talk about the problem now.
Okay.
Yes,
You can divide the square up into 4 squares, which each
exactly.
have
So
1
this
centimeter.
is the crucial point. Sorry for interrupting, but this is the crucial point. So Emily is actually telling us that we divide this square into 4 parts. Let me change my color here. So why 4? Can you tell us how did you come to this idea that you wanted to divide it into 4, for example, not
We have,
more or
we have
less?
5 points in total,
Yeah,
and we have 4 segments. Then we know that at
yes.
least 2 points will be in the same segment.
Okay, so you see, this is somehow a hint in the problem itself. I'm not saying that this is always the case, but when you have 5 points, it means, and if you understand that these 5 points somehow are going to play the role of the pigeons, then if you want to use the pigeonhole principle, you need to have at most 4 pigeonholes. And usually most of these problems, they differ exactly by 1. So by looking at these 5 and trying to find a way to give the role of pigeons to these 5 points, then I would say to myself, okay, is there any way that I can have 4 pigeonholes? And then in this way of thinking, might be it is not hard to realize that we divide our square into 4 regions by imagining this cut. This cut is not there. I am just imagining it in my head. Okay, now can you, Emil, continue yourself? Okay, then what?
Okay, so you're gonna have, if you place 5 points randomly, there's gonna be at least 2 points within the same area or within the same little square.
Yes,
And in
yes,
the absolute worst case scenario, they're in one corner each
yes.
of the small square. And the distance between them then is the Pythagoras of
Exactly, exactly. Thank you very much. So that is exactly the idea. So he is telling, okay, I partition this square into 4 smaller blocks, and regions is better, in my head, of course. And then how many points I have? I have 5 points. But how, I will give the role of pigeonholes to these regions. I have 4 of them, but I have 5 points. So it means that it doesn't matter how I choose these 5 points, because the number of points is bigger than the number of regions. There is at least one partition which contains 2 or more points. Let alone having more points, at least I have 2 points. And actually, Emily expressed it in a very nice way. He said that if I have these 2 points, here, 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 it doesn't matter. The argument remains the same. And then he said that the worst possible scenario is that I am very unlucky that one of them here, one of them is there, because this is the longest distance between 2 points belonging to the same partition. Yes. And then this, we know what is the highest value of this distance is that this diagonal. And then we, using Pythagoras theorem, we know that this is 1 because the whole is 2, and this is also 1, and this is a right angle triangle. Using Pythagoras theorem, you realize that this is a square root of 2. So if I am completely unlucky, then these 2 are chosen, then the distance is a square root of 2. But always the distance is either square root of 2 or less than square root of 2. So it means that definitely 2 of these points have this property. When I measure the distance of these 2 points from each other, it is at most square root of 2. I don't want to write it down to spend time on it, but in principle, you need to be able to write it down. Okay. So you might say that, okay, we divide the square into 4 equal squares as shown in the picture, since we choose 5 points, and we have only 4 partitions, there is at least one partition that contains 2 or more points. But the largest distance of a pair of points in a partition is at most square root of 2, and then you can say by Pythagoras theorem, and then yeah, just 1 or 2 sentences. So this means that this is true or whatever. So you need to start something like this, or any other sentences that you want to use on your own. But it is always good, yeah, it is always good to say that, okay, in principle, if this is, I don't know, is a national exam, it is better to mention the role of the pigeon and then the role of the pigeonholes, make it clear, and then say that I am using the pigeonhole principle. Okay, but the idea is just what I told you. Is there any questions here? Okay, now that you have some experience about this type of problems, let us go back to this problem that I made a mistake when I was writing it down. Okay, so here now I have an equilateral triangle whose length is 1 meter. So let me just draw one of them. Okay, so let us see if I can do it properly here. So assume that this is a equilateral triangle. So all sides have length. Of course, this picture is not probably the a good one. Okay. Okay, so I have an equilateral triangle. I know that the sides each is 1 meter. Now I am choosing 10 points randomly or whatever from the interior of this triangle. And then I want to show that there is at least a pair of points from the points that I am choosing randomly, whose distance from each other is at most 1/3 of meter. If you listen to me, when Emil solved the problem, I told you that somehow this number gives you a hint. This is my experience. Of course, in this problem, if they want to bother you a little bit, they could mention 12 points. Then you might always think to make the partition so that I have 11 partitions, but no. So usually they don't do like this, but even I could immediately say that I have 12 points, and the reasoning that I want to present for you remains the same. Okay, any idea how to solve this problem?
Mr. Babak, you can do like a divide it into 4 smaller triangles.
Okay, if you say 4, then what?
No, not yeah, exactly like that. And then you can split them all of the 4 triangles once again into half. Because then it would be 8, right?
Then it would be 8, but I need 10, and the other point is that I need to give a roll somehow to this number, a third.
Yeah. But
so if you do this, this is 1/2. This is 1/2. All of them are 1/2 actually. Yeah. Okay. And then okay, and then I am choosing 10 points. So you are saying that if I do this once more.
But then it becomes too many. I mean, just
yeah, it becomes too
arbitrarily
many.
through the half. So from the top of the triangle, you do like a line down to the bottom.
Yes.
Yeah, and then you do the same thing as before with the like first you do, yeah, exactly, and then you can also
Okay,
split
then.
the left and the right side. Like there's a big left triangle and a big right triangle that's still not
So
divided
you
into
have
half.
1, 2, 3, 4, 5, 6 now.
No, I mean the you can draw. There are two triangles that are bigger than the other four, right? You can also divide them into
Yes.
two.
How I should divide it by 2?
From
Oh, what
the
one thing is that you shouldn't, first of all, let me tell you, because if this is going to be like that, it means that the person who has designed the question was thinking very, very particular case. What I advise you is that at least shouldn't be the first tackle to the problem. You need to try to think symmetrically first. If, of course, the problem is hard, I agree with you, then might be these simple arguments will not work. Then you need to come up with a more complicated partition. So at least for these problems at this level, I don't recommend you to think about those. Is there any nicer way that you can have 10 partitions of this equilateral triangle?
Yes.
I want to have 9 partitions, by the way, because the number of points is 10. Who said yes?
Me again.
Okay, so anyone else except Emil and except Alex now? Do you want to
I have an
participate?
idea.
Yeah, yes. Who is talking? Sorry.
Carl,
Okay, Carl. Okay.
maybe we can start off by dividing each side into 3.
Uh-huh. So let me
Then,
do that. So you are saying that dividing by equal parts. Yes, of course.
yes,
Okay. So assume that these are all equal. Of course, my picture is not very good, but you understand what I mean. Then what?
then we can use that to like draw 9 equilateral triangles within that triangle.
Can you guide me how? So how should I, which one, for example, should I connect these?
Yes.
And then I should connect this and this and that and this and this, yes? How many?
Yes.
1, 2, 3, 4, 5, 6, 7, 8, 9. That's good. Yes, yes, that's working. So if you see, this picture is completely symmetric. I don't need to bother about the sizes and everything because all of them are identical from size point of view. So yes, I would go for it. So let me just make it more clear. So what Carl is saying is that we divide each length to 1/3. Actually, this is actually somehow helping us, yes, because the side was 1, and then we want to talk about 1/3. So might be the most natural thing comes to mind is to partition, to divide each one side. Of course, I don't know, this is not very good, but yeah. So let me just do it a little bit of like this. So yeah, this is a very bad picture. So no, it is not good. So let me try to see if I can do a little bit better. I don't have enough tool here. Yes, so I think, so these 2 points. So let me just, yeah, let me just this point and that point. Yeah, and this point and that point and this point and that one. Anyway, this is not going to work if I want to be very precise here. Okay, so at least this is understandable. Okay, so here we partition into in this way. So each one of them is 1/3 actually. Okay, now how many triangles you see? I have 1, 2, 3, 4, 5, 6, 7, 8, and 9. Yeah, that's exactly the case. And I have 10 points. Okay, so 10 are actually, these points are playing the role of the pigeons. These partitions that are 9 of them are playing the role of the pigeonholes. And I choose 10 of them. So it means that at least one of these partitions, which one I don't know, at least one of these partitions will receive 2 or more points. Let us, for example, for definiteness of discussion, let us just concentrate here. Assume that this is the one which is receiving at least 2 points. So it means that I have 2 points inside this region, okay? But what is the maximum in the worst case scenario? What is the maximum distance of these 2 points in each one of these single partitions? It is clear that this length is at most a third. Is that clear? I don't know.
Yes.
This is, I think, easy. Might be, I don't know. I couldn't imagine anything else. So you might be able to cook up another argument by another type of partitioning. I'm not saying that this is not possible, but I'm saying that this is probably the easiest possible partition that comes to mind, especially by looking at these 2 numbers and this number 10. Okay, so that is one way of arguing for this problem. Okay. If you don't have any questions, now let us go to these 2 problems that we have today. So how much? One problem is left. Yes, only one problem is left. And this is a very nice problem. Actually, I had a little bit problem when I wanted to solve it myself. Any one of you can, so let me read the question for you now. Consider 6 arbitrary points on a plane. So I have a plane, goes to infinity from all directions. I choose 6 random points, I would say, arbitrary points on this plane. We connect every pair of points to each other by straight line segments, and we paint each line segment in red or blue randomly. Prove that there exists a monochromatic chromatic triangle. Monochromatic triangle, yes. So you know that what's the meaning of monochromatic triangle, yes?
Only one color.
Yes, it means that definitely there is a triangle whose all sides are colored in red, or there is a triangle whose sides are all colored in blue. So I have 6 points randomly chosen. So the plane is not playing a role here actually that much. Yes, the reason that they are saying that we choose 6 points in a plane, because if these points are not in the plane, I don't think that is a problem. Yes. No, even so, it might happen that some of these triangles are in a space. Yeah, but so don't concentrate on that part. The important part is that we have 6 points chosen, and we start connecting all these points pairwise together. For example, if I want to give you an idea, A, B, C, D, E, F, G. No, sorry, E, F. A, B, C, D, E, F. 6 points. I connect A to these points, and then I go to B. I connect it to all of them. And I do the same thing for C, you know. So I connect every pair to each other, and I start coloring each one of these line segments randomly in blue or red. I want to prove that how you do it, it doesn't matter. You definitely have a monochromatic triangle. Do you have any kind of argument for this?
As long as there exists 3 points of the same color, we have, by definition, since every point is connected to every point, we have.
But the points are not colored.
Triangle.
Be careful. The points are not colored.
I mean, line segments. As long as they're
okay. Okay, but then you know that because these questions, the statement of these questions are simple. So you need to have an argument. So everyone should totally be convinced about the argument. It should be very firm and rigid, you know.
Actually, my argument doesn't work because it was using points, not lines.
Okay. Anyone else? Yeah, it is not that clear how to use the pigeonhole principle. I don't know why what they are doing in the kitchen. Okay. Let me because it was an interesting problem for me. So let us concentrate. Let us give the point's name. Okay, this is point A, this is point B, and it is mentioned it is on the plane, so it is not. So let us A, B, C, and D, and E, and F. So this is the situation. Yeah, I'm just picturing it. We don't know exactly, but these are 6 points chosen. I think one thing, instead of saying it on plane, they should mention that none of the 3 points lie on the same line. I think the person who actually wrote this in a book, I think, they should mention that none of these 3 points lie on the same line, because otherwise we don't have any triangle if I connect them. Okay, so let us consider like this exactly. Let us not make the problem hard. And let me concentrate on one of these points. For example, point A. I don't need to draw all the lines to make the problem hard for myself. I just take A, and I know that A is connected to all these points according to what is mentioned in the problem. So A is definitely connected to B. It's also connected to C, and it is connected to D. Yes, and it is to E.
Mr. Babak,
Yes.
after this, I think there might be a proof without using the pigeonhole theory, but maybe it doesn't work. I don't know.
No, let me concentrate here, and then I will come back to your argument if you have one. So these are the lines. Okay, so can you tell me, first of all, can all of them be of different colors? Apparently not. Yes, because I have only 2 colors, red or blue. I have red or blue in one of them. Okay, but one thing is important. I have 1, 2, 3, 4, 5 pigeonholes. 5 pigeonholes. Okay, and I have 2 colors, 2 pigeons. So how many of these pigeonholes receive the same color? Can you say something about the number of colors, the number of edges with the same color?
3 and 2.
So I mean, this is the inevitable. Yes, it might happen that all of them are red. This is possible, but at least 3 of these lines are of the same color. Do you agree with me or not?
Yes.
Yes, everyone. So I have 5 edges. I have 2 colors available, and I start coloring these with red or blue. What I am claiming is, how you do it, it is not important. 3 of these lines have the same color. Do you agree with me?
Yes.
This is the pigeonhole principle, because I would say that, okay, I put I have it red, and then this next one is blue. I want to consider the worst possible case scenario. Then I will make this red and then blue. The next one becomes red or blue. It doesn't matter. So in any case, I will have either 3 blue or 3 red. This is inevitable, and that is the way that I am using the pigeonhole principle. Yes. So for example, I will say that this is blue. This is blue. This is also blue. I don't know, for example. This is also blue. And then let us assume that this is red and this is red. Okay. What is important is that at least there are 3 out of these five, there are 3 of them having the same color. For definiteness of argument, I assumed here that 3 of them are blue. When I finish my reasoning, you will understand that it doesn't matter. I could have assumed that 3 of them are red, and it doesn't matter which ones are the same color. Here I have chosen this B, 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 and B. I could write this B, and this B. It doesn't matter. You will see it. But I don't want to continue. Can you cook up the continuation? Can you cook up an argument after this?
If we pick one of the other points, which is also blue, there are 2 other points it could connect to that are also blue.
Are you talking about points or lines? Because I'm confused.
Yeah, I mean, like if we take one point that has a blue line segment, then there are only 2 other points which also have a blue line segment, and therefore, no, wait, that doesn't work.
No, because I want to have a triangle yet. A monochromatic triangle. I don't have that triangle yet. Just think a little bit. It is not hard. Another guide. Look at this edge now.
I think I have an idea.
Yes, please.
If we connect, for example, B to E, it doesn't matter which color it is. It will create the monochromatic. Like, it doesn't matter what color the line segment is. It will create the monochromatic triangle.
You mean B to E, you said?
Yes.
Okay, why are you sure about that? Because how do you know that? If this is red, you are right. If this turns out to be red, then this is red, this is red, this is red. So this is a monochromatic triangle whose sides are red. But how do you know that? It might happen that it is blue.
Well, it intersects those other 2. Like
No. This is not. Yeah, I understand what you mean. If you say this is blue, then you cannot say that this one with this one and this one is blue. Yes?
Okay.
Yes, that is not working, but you were a little bit close. But I was thinking, okay, let us think in my way, okay, if you don't mind. Let us this idea is good. Now start reasoning. And this is a very nice problem, by the way. So if I connect this one to this one, how many possibilities are there for the color of this one?
2.
2, either blue or red. If it is blue, I am done. Do you agree?
Yep.
Because this one is my monochromatic triangle. All of them are blue. Okay, but there is no guarantee that this is blue. It might happen that this is red. So what I'm trying to say, let me start doing it. So I will draw with a neutral color. Okay, so let us just choose gray. I connect these 2 points. If this is blue, then I am done. But so let us assume that this is in contrary red. Okay, then cook up the argument. If it is blue, I am done. If it is red, how can I continue the argument? Okay, so the time is finishing. Let me complete it. If this is blue, I am done. If it is red, I need to continue the argument. So assume that this is indeed red. What I do, I will now connect these 2. Okay? If this turns out to be blue, I am done, yes? Because now this is a monochromatic one. So if this turns out to be blue, I am done. So assume that this is not the case and this one is also red. Can you finalize the problem now? No. Okay, so then I consider here again. Again, how many possibilities are there for this one? I don't know why this is making this. Okay, so I have two possibilities for this new one, either blue or red. If this is blue, again, I am done. Why? Because now this is my monochromatic triangle. But so assume that this is not the case and this is red. Okay, in that case, this is my monochromatic triangle with all of them are. So still I have it. Do you understand what's going on? So it's a very nice problem. So what I'm saying is that 3 of them are of the same color. Okay, this is definitely clear because of the pigeonhole principle. And now I concentrate on this triangle here. Okay, if one of these legs is blue, then that leg with these 2 legs gives me the monochromatic triangle. If none of these are blue, it means that all of them are red. Then this one itself becomes the monochromatic triangle. So in either case, it is guaranteed that I will have at least one monochromatic triangle. And hopefully you will see that this argument doesn't depend on how many of them are blue, how many of them are red, or which one are blue and which one are red. You can just cook up another scenario for yourself and try to convince yourself that this is also working in this case. Okay, any specific questions? This is one of those problems you need to do it once for yourself to understand what's going on. And of course, I haven't written something down. You can just review this video again if you don't understand what's going. But if you have any problem, yes?
On a test, suppose we were to get this question, would you have to like write, like we're assuming that the line FA, like in words, or could a picture be used somehow to?
Yes, I think it's better to use a picture to illuminate, but you don't need to be worried about writing this. This is much higher than the level of the problems in the book, but so this is why I'm saying that just focus on learn and enjoying the problem. So did you learn what is the, did you understand that this proof is a really firm and rigid proof? Yes. Yep. Yeah. So this tells you that okay, I have 3 colors, then let me look at these points and connect them together. If if one of these legs are of the same color, then I have my chromatic triangle. If none of them are of that color, then this triangle itself is my monochromatic triangle. So that is the core of this reasoning. Okay. Okay, so we are actually a little bit exceeding the time. So if you don't have any questions, I stop this video here.